Hello everyone, yes, my name is Olivia and I work as a machine learning scientist at Flagship. For those that don't know Flagship is a venture creation firm based in Boston, and we create startups. The most popular one was the vaccine maker Moderna. I'm a member of the Pioneering Intelligence team, which is our in-house machine learning team where we prototype machine learning methods and we try to validate them for new computational platforms that we might want to turn into startups or to support our early stage startups. So over the last 2 years, I got in touch with a lot of reinforcement learning methods that I applied to generative biomolecular design. So today I want to give a little bit of an overview on how reinforcement learning is used for generative biomolecular design, and also tell you a little bit about some pitfalls, where it makes sense, what are a couple of tricks. And this is supposed to be practical, so after giving a brief overview of RL methods, I really want to dive into specific biomolecular design case studies so that you get a feeling on what different problems you might be able to attack with reinforcement learning. So before I dive into methods, I just want to briefly give a little bit of an introduction of reinforcement learning versus reinforcement fine-tuning. So this talk will not be about classical reinforcement learning. If you look up online what the definition is of RL, on Wikipedia you find that RL is an area of machine learning concerned with how an intelligent agent ought to take actions in a dynamic environment in order to maximize the cumulative reward. And this is also usually how people think about RL. They think there is an intelligent agent, that's usually a network, and that agent is in a state and can take actions A to get to another state S, interacting in this environment. And there's an associated transition probability that gets the agent from state S to state S prime via an action A, and then there's a reward that is associated from getting from S to S prime, and this is how the agent over time learns. This has been very successful in games, and if you look into reinforcement learning literature, there's a lot from the 90s and the 2000s. They all benchmark themselves against games. Particularly the popular ones are Atari, or there's Minecraft. OpenAI has a fantastic RL gym where they provide all these games that you can benchmark your reinforcement learning algorithm against. And 2016 was a very popular year for Google DeepMind, where they published AlphaGo, which was a reinforcement learning model to play a game Go. And it beat the world champion in Go. I think his name was Lee Segol. And it was actually my partner who a couple of weeks ago told me that this guy stopped playing Go afterwards. So I looked this up, and apparently 3 years later he retired from playing Go, and he said, there's no point in playing Go anymore because there's an entity that I cannot beat. And I think this is a little bit sad because it was an unfair competition. Because if you look at RL in games, playing against a human is a little bit of an unfair game because AlphaGo was trained on millions of games, and it also did self-replay. The human player, I'm sure he didn't do millions of games. So this is a little bit where the success is coming from RL in games is RL in games can bootstrap intelligence from scratch because it has infinite data. Because playing games it's cheap simulations, it's easy to do, somewhat easy. But bootstrapping biological intelligence from the data there is, I think, is absolutely delusional, because biology is data scarce and data sparse, and learning the rules of biology, which is incredibly complex, from scratch, I think, is more or less impossible with the data we have. So in terms of sparse is, if we look at the amount of protein sequences that we have found, they're in the range of billions. Protein sequences are between 10 and thousands amino acid longs. The vocabulary is 20 canonical amino acids. That combinatorial space is huge. We have measured around 300,000 structures for these. If you look at the small molecule space, people usually quote a combinatorial space of 10 to the power of 60. So the amount of data is not there to learn that from scratch. However, RL is excellent for black box optimization, and this is a little bit where its strength is coming from. So for the remainder of this talk, I want you to replace the notion of an intelligent agent with a pre-trained policy, a generative network that is tuned to a specific goal. So the pre-trained policy could be anything. It could be a protein large language model, chemistry large language model, small molecule diffusion, and you can extend that. And there are a lot of black boxes in biology where we do not know the complex mechanisms. Black box could, and we can use RL to distill the heuristics of that black box into our pre-trained policy. So black boxes can be human preferences. So I had a colleague who came to me, can you please have your inverse folding model to avoid methionine? Because he didn't like it, because in his experiments it always messed up, it always unraveled. Another feedback could be simulation. If it docks in the simulation, you can't back propagate through a simulation, it's non-differentiable. Experimental feedback, similar to the molecules that were synthesizable and soluble in our experiments. Other feedback that could, in theory, be differentiable is maybe another very big model. Maybe you want to distill knowledge from like a big model like AlphaFold into your pre-trained policy. In theory, you could extend that to your training, to your network, but it becomes practically a bit prohibitive because at some point it gets so big and you get vanishing gradients, it becomes very clunky, and so on. This is where RL shines because we can directly give that feedback without having to be able to differentiate. So in biology, we tend to do reinforcement tuning rather than reinforcement learning from scratch. So a brief review of methods that I will touch upon in the examples that we will go over. So RL has like a very colorful bouquet of methods. And they're model-based and model-free ones. We're completely going to ignore the model-based ones. We're just going to focus on model-free. And there we're also going to ignore all the Q-learning that I'm actually lucky that Mia in the previous talk touched upon a bit. The Q-learning is a value-based. A lot of games are value-based where you learn a value function. But I'm going to focus on the policy gradient methods, which are directly optimizing the policy. Very popular is PPO, proximal policy optimization, trust region, PO. DPO came out about a year or two ago. It's direct preference optimization. There's DDPO, which is a diffusion version of PPO. And then it shouldn't be under the policy optimization. There are non-policy methods that I very briefly want to touch upon at the very end. And I want to talk about generative flow networks. So policy gradients. The objective in policy gradient methods is to update the policy pi such that high reward values A become more likely. The policy is updated by gradient ascent towards the expected reward. So this is already a little bit just to wrap your head around. You're so trained as a machine learning scientist to do gradient descent. Here we're doing gradient ascent. And it looks a little bit like this. So you try to maximize an expected reward of taking an action A to achieve a reward. So if your reward, or here we call it advantage A, we use that interchangeably, if that one is positive and high, you want to walk up your gradient towards taking that action. If it's negative, you want to walk away from there. So you can already feel, and Matt touched upon this a little bit in the beginning, there is a lot of finicky engineering going into RL. A lot of work can actually just go into what we call reward shaping, into how to normalize this, should you do plus minus, should you do ranking, and so on. So there are many roads that lead to Rome, and there are many derivatives of the policy gradient. Often people just add another term and give it a new name. So the most popular one is proximal policy optimization, where the trick is you look at the ratio of your updated policy and your old policy, and what is the likelihood of that action being taken under the updated and old policy, and is that a state you want to be in with like high positive reward or no. This is how this the gradient. This is how the loss is defined. This is how you actually get something that is differentiable and that you can learn from. In practice, you do that with a clipped version of that loss. It's called clip PPO, because what you want to avoid, it's really brute force kind of way of updating your gradient. It's only done by like this ratio and the magnitude of this reward. So what can easily happen is that you fall off the cliff. So you want to clip your update steps. There's another way to do that is with trust region PO, where you add a Kullback-Leibler divergence between your old and your new policy that basically prevents you from updating away too much from your original policy and completely unlearning what you originally had already learned in your policy. Another thing I need to introduce you to is this idea of taking multiple actions is not necessarily valid for every kind of policy. So if you think about a large language model that is trained with a causal transformer, so where you have like a left to right logic, but it's just a one-step prediction. So you have one action to take and one outcome. If you think about autoregressive sampling, you have multiple ways to like sample a word or a token. There you have multiple actions to take and multiple steps. So there can be sequential actions or only one single action. Rewards can be cumulative or they can just be a single reward. So to give you just a little bit of a spiel on how you can then translate that to different tasks. So in a game, your state would be an environment, and here the example is you're facing a corner. The action that your agent could take could be to turn right, or maybe to turn left. The policy determines the probability of turning right given you're facing a corner, and then there's an associated reward with it, usually at the end of the game if you, for example, made it through a maze or whatever. Another very popular example is reinforcement learning with human feedback, RLHF, which became incredibly popular with OpenAI using it to align their GPTs towards human preference and being more ethical. And the way that it works here now, you don't have an environment anymore. Ditch the environment. You have an input query or a prompt, in this case, tell me about the moon. And your policy, that's the large language model, can give you different outputs. Usually you can achieve that, for example, via temperature sampling. An action could be, the moon is big. Another action output could be, the moon is orbiting the Earth. Another one could be, the moon is baked. So now how do you assign rewards? How it's done here is they rank it. What is the most relevant, most appropriate answer to my query here? And here we say, okay, the moon is orbiting the Earth is better than the moon is big, which is also better than the moon is baked. Now you get a ranking. This is how you can shape this reward and how you can define your differentiable loss in PPO. Now an example from biology, protein folding. I hope you all attended the AlphaFold 3 talk yesterday. So that is also a generative policy where now your state is a sequence, that's the input to your model, and the action is to predict the 3D structure that belongs to that protein sequence. So your policy is a folding model. Your advantage or reward is, for example, an RMSD match between the predicted structure and the ground truth structure. Okay. So now that you know policy gradients, you're actually more or less ready to go to dive into a bunch of different use cases. So the first one that I want to discuss is protein inverse folding. So again, for those that attended the protein forward folding talk yesterday of AlphaFold 3, now we're trying to do the reverse. So protein inverse folding models learn to approximate the probability, the likelihood of a sequence given an input structure. So you give as an input your protein structure, usually just the so-called backbone, and you want your model to produce a sequence that would fold into that structure. And a very important point here is to note that this is a one-to-many problem. So for a given structure, there are multiple solutions. There are many sequences that can fold into one structure. This is somewhat size dependent. If you think about a very simple alpha helix, there are very many sequences that fold into that simple alpha helix. Once they become more complex, and you can think like big nanopores, etc., with many chains, etc., there might be less. Why is this important to actually get at the many to the one? Because if you find one sequence, that you're done, right? That's not very much true, because you have to imagine this is the very beginning of protein drug design. Once you have your sequence candidates, you go along a very long filtering process where you have computational filters that will rule out all the proteins that you already from computational filters know might not be stable, etc. Then you will go into an animal study, then you will go into clinical trials, and so on and so on and so on. At the very end, you're usually left, if you're lucky, with a hit rate of 1 or 2. So ideally, you want to maximize your chances by starting with as many viable candidates as possible. The other more practical point behind this is patenting. So if you make a hit at the very end, that's great, you're going to patent it. But if you spend all the money on dev and you go through clinical trials, you also kind of want to make sure that tomorrow your competitor is not going to come out with something that does exactly the same thing. So two different explanations why you want to get to the many to the one. So to learn protein inverse folding, we use data from the protein data bank. Those are structure sequence pairs. However, as I mentioned earlier, the data is sparse. We have around, it's actually not exactly 300,000 measured structure sequence pairs. It's actually less. I think it's like 250 around now. They're always adding. The training is done on these structure sequence pairs. 300,000 or 250,000 is just an absolutely tiny drop in the ocean if you think about that huge combinatorial space of 20 amino acid types and the length 10 to thousands. So you can really think about this being kind of like a protein universe where there is a lot of space where there is like nothing measured. And the truth is there might also be nothing stable. So we really don't really know what is out there. And it's really hard for us to, or we don't really, with that data, we will definitely not learn the ground truth distribution. So what happens if we then train inverse folding? In practice, at inference of running these models is that you often generate sequences that do not fold into the original structure perfectly. And also, you don't find all of the solutions. So the question here is, what if RL can update inverse folding models to generate more foldable, diverse proteins? So let's take a look at the first approach. We're going to do protein inverse folding with protein MPNM and PPO. So I chose protein MPNN because protein MPNN for protein designers is like a go-to inverse folding model. It has become very popular. It comes out of David Baker's lab. And this is an autoregressive policy where your input is the structure, then you have it's based on a graph neural network, and then you have an autoregressive sampling in any order. So for the human language NLP people in the audience, we can do decoding in any order. There's not necessarily a left-right logic and biological sequences. We can actually take advantage of being able to decode this sequence, like starting in the middle, hopping to the front, going to the end, and so on. This is also how you can create diversity in your solutions. That's how this model works. But the observation is that in practice, the model often generates sequences that don't fold into this input structure X perfectly, and the model is lacking diversity. So what could we do? We could give structural feedback by folding sequences forward. So we can take the generated sequences, take a good folding model like AlphaFold 3, or if you have a lot of money, you could go to the lab and try to express these proteins and see if they fold and measure them. And then we can compare how do they compare to the ground truth structure. So here you see in blue, this is a folded sequence. That sequence was generated from the policy, we fold it, and we see it's not a perfect match to the ground truth, which is in red. On the right-hand side, we see a sequence that looks slightly different. If we forward fold it, it's a pretty good match to the original one. So we use the so-called TM score, which stands for Template Modeling Score, which is better than RMSD because it's designed to capture global and local alignment in a better way than like an RMSD would do. And TM score of 1 means perfect match, TM score of 0 is absolutely horrible. TM score of 0.5 starts to getting more okay. A biologist would already start getting happy with 0.7 because this is where structures start to be what they call of the same fold. So that they're somewhat similar, so you expect them to have the same or a similar function, which is in the end what you're getting for the reason why we want to be so good at predicting structure is because the structure determines the function of that protein. So we can give that TM score, we could use the AlphaFold as our forward folding model and backpropagate end to end. In practice, this is really not straightforward. So instead, we can do black box optimization with PPO. So we just forward fold and we just return the folding score back to the policy. And this is what it looks like. So here in the beginning, what I show you here is a true ground truth structure. We put that structure into a protein MPNN. It gives us a sequence. We forward fold it, and you can see this is not a very good match to the ground truth structure. This is at epoch 0, so no training has happened, no feedback. So we start training with the TM score structural feedback, and at epoch 1 we already see a little bit of improvement. And then as we continue training, this is the PPO fine-tuning, as the epochs progress, we get better and better in producing sequences that, when we forward fold them, start to align better with the ground truth structure. So we're getting sequences that, according to our folding proxy, likely will have a similar function. So another example that I want to show here is doing thermal stability. So what I just showed you was the structural feedback. Another very important factor for proteins is thermal stability. Proteins unravel at increasing temperatures, and ideally you want a protein's melting temperature to be as high as possible, because when it unravels, it's completely useless, has no function anymore. And there are machine learning in silico proxy models that estimate the thermal stability for a sequence. So you give the sequence to the model, and it estimates the melting temperature in Celsius. So when we do that, so here we took protein MPNN and we do the same PPO feedback with the thermal stability. So now we score the thermal stability values of the generated sequences. We observe something that is very, very common for PPO that everyone in any field, human languages, biology, complains about policy gradient methods, is that they do what they're supposed to do, what they say on the tin. They maximize a reward. So they really dig into that minimum of getting to high reward. So they get really good at this feedback task, but they forget everything else. So here we observe that we can very easily push PPO to give us super stable protein sequences according to this proxy. So here we have a protein from the protein data bank. This is its original structure. It has a melting temperature of 44 according to the thermal stability model. We give that structure to protein MPNN that will produce a sequence for us. But this is the protein MPNN that has been PPO'd with the thermal stability model. So we get a sequence, and that one has a really crazy high melting temperature. It's almost, you can already be suspicious here, that this is very high. And now we forward fold it, and we see exactly what many people observe is that it gets really good at getting the reward, but it leads to catastrophic forgetting. So now if we fold it forward, it's really not matching the ground truth structure anymore and starts to unravel. So one option is to use a KL term to make sure you're not diverging too much from your protein MPNN original policy. That then leads you to actually not really being able to learn the thermal stability proxy. So we did a multi-objective between the two. And if you treat it as a multi-objective, so you give structural feedback, you give a thermal feedback, put it all together in your loss, you can find a middle ground where you get decent melting temperature, and you're still able to generate sequences that fold into the original one. So that is something you can do. So now I want to switch the generative approach from the autoregressive model protein MPNN to diffusion. And I'm going to stay in the same domain of protein inverse folding because there are very many different ways to do protein inverse folding, and maybe some of them are better for RL. So, brief review of diffusion, and I'm sure you guys have seen this many times. Diffusion is where you have a forward noising process. You start with your ground truth distribution of data. You iteratively add noise until it's fully noised, and at each step you have a network that is trying to estimate the noise term. And then you have a denoising backward process, which is the sampling, where you then start with noise, you iteratively remove the noise term, and you hope to, or you do generate a point that is within the distribution of your training data. And this is what the process looks like. It's a step-by-step process. So you have a training algorithm where you add noise and learn the noise term, and then you have a sampling algorithm where you recover a data point from noise. And it's this sampling policy, it's this network that you can perform reinforcement learning on. So policy gradient and diffusion, it's called denoising diffusion policy optimization, PPO. So here on the top, that's the generic denoising formula, and I added in a condition just to prime you a little bit for the inverse folding task where you have a structure condition. And the expected reward in the policy gradient is you want to maximize the expected reward of that data point that you recover from the noised to the denoised state. And in DDPO, it defines a policy gradient on the denoising network P with multi-step optimization to maximize the reward. So here you already see this looks a little bit similar to the PPO ratio. But now here, I really want to emphasize this because this is how you implement it. It's a multi-step optimization, so it makes it somewhat efficient. So you are optimizing at each step of the denoising network here. Okay, so let's take a look how that looks like for protein inverse folding. So this is work that I did with my colleagues Sid, who actually now works at Future House, and with Yasha Ektifaya, who's a PhD student at Harvard. So we wanted to get at this problem of finding as many solutions to a structure and finding all the diverse space of it. And we hypothesized that a better way of doing this is using categorical diffusion. So categorical diffusion works, you can imagine it this way. You still have your input structure, and you have an associated sequence from the ground truth. And now you treat this as a noising process, where at each step you are adding noise to your distribution. So you have a one-hot encoding for each amino acid, and you can see at time t0, this is very discrete. And then at each step, you're making them more and more evenly distributed by applying these Q matrices, which are transition matrices of your vocab size, in this case 20 by 10. And again, the goal of this pre-training is to find more diverse solutions to the inverse folding problem. We call this model diff, like diffusion inverse folding. And if we compare it to other methods, particularly protein MPNN, which is a popular method, we see that we get a diversity of 45% compared to 25%. 45% it's a comparison on each position. It means at each positions you get 45%, or you get different amino acid types at 45% of the positions. But the sad thing that we saw training it this way was that our so-called TM score, so that's the structural similarity score, had gone down. So we were producing very diverse sequences, but they were not as good as actually folding into the ground truth anymore. So we were okay, let's take RL to the rescue. It can fix it, hopefully. So we added a second training phase where we take this pre-trained policy and run DDPO, this diffusion way of doing PPO with a folding server pool. And here are the results. So after doing that, we were able to run a couple of epochs to get those sequences back to fold as nicely as the other methods. We lost a little bit of diversity here, which is actually one of the observations that people think that RL can explore novel solutions for you, but I don't think this is the case in these spaces because I think the solution is very unsmooth, and what is rather happening is that it's going to focus on the one that gives it high reward. So you actually end up losing a little bit of diversity by doing that. What does that look like in results? So here I'm coming back to this simple alpha helix. As I said in the beginning, there are very many sequences that fold into this very simple structure. On the bottom here, this is protein MPNN. We take the alpha helix and we query it and to give us 4 sequences for the alpha helix. They all fold very nicely, so what you see here in green and in orange is actually a perfect match of the forward folded sequences and the ground truth. But all of these sequences are very similar. You see a few positions where they differ. When we look at the RL version of the categorical diffusion inverse folding, we also get sequences that very nicely fold into the ground truth, but if you look at the diversity, it is much, much more diverse. Similarly, if we look at more complex structures, so this is now like a mid-sized structure, we see the same. We're able to recover the original structure, but we get more diverse solutions than the protein-ampidin comparison. Okay, now I want to jump space from proteins to small molecules. So here I want to talk about small molecule design and using RL on diffusion there as well. So a brief review on what small molecules are and what you have to do to run diffusion as a generative policy for small molecules. So if you have never dealt with small molecules before, I think a very naive but helpful way to think about what a small molecule is, it's a graph of atoms that are connected by bonds. So here you see a graph. This is a 2D graph of a molecule called latanoprost. Has atom types where they're not marked, that's a carbon C. And they have bonds. This is an aromatic ring bond. There are double bonds, there are single bonds. This is the 2D version of it. This 2D graph has multiple 3D point clouds associated with it. And those are called conformers. This is what you see to the right. So in nature, this 2D graph is actually able to have like different conformations, but and different degrees of freedom. So you will usually find that something like the aromatic ring, which we also like to call a fragment, that guy will never like twist into itself, but you will see that there are more flexible points where this part could like, you know, come out here or go into the screen. And all these different 3D structures, they're important because they're all associated with energy. And as you know, in nature prefers things that minimize energy. So this also is important to know, like what molecule can have a conformer that can, you know, is energetically favorable, or if you want to do docking, that's also very important. So ideally, we want to have a generative small molecule model that can create and learn these conformational structures. So again, we treat this as a 3D point cloud. And the features are atoms. So we need two ingredients, or we need one major ingredient and one bystander ingredient. The first one is Gaussian diffusion on the coordinates and on the features. So you start with this 3D conformer, and then you do Gaussian diffusion on the coordinates x, y, z, and you also do diffusion on the atomic feature vector, which is just simply some one-hot encoded vector. Another ingredient, which people are debating a lot about to what degree is it useful or not, it's a pure question of how much data you have, is baking in some physical knowledge, some symmetry knowledge. So we usually use rotationally equivariant networks. The idea here is that no matter how you rotate your molecule in your output space, that should be independent how it's represented by the network. So no matter, like if I were to rotate my completely noise point cloud, that should be translatable in the output. I think you get that. So now let's put this into a concrete biomolecular design use case. So just generating small molecules with diffusion is not that useful because biology happens when two objects come together and interact. And a very common or popular design case would be to design a ligand, which is a small molecule, that binds to a protein to perform some function. So this is work that I did with my colleague Sid Narayanan. So here we did some pre-training with all atom diffusion for small molecules, as I just described. We then fine-tuned that policy. So this pre-trained policy just knows what small molecules look like. We fine-tune it to start to know what do small molecules look like in the presence of a protein pocket. So we fine-tune with data from the protein data bank, where there are a bunch of examples, like on the order of I think 20,000 protein pockets with the ligands in it. So the binding pocket in this case is also an all-atom representation, but it's fixed, it's not being noised. So at sampling time, your input is noise plus the binding pocket, and the output will be one of these 3D conformers. And you can sample this as many times as you like. So in practice, and people talked around about this already, molecular docking. So it is very important to know how a molecule is binding into a protein and to calculate the associated energy to infer if this is actually going to stay there, if it's going to bind, and what the associated binding affinity is. And there are a bunch of in silico docking models, and to be honest, they're all not very great. So you should take them with a grain of salt. They get a lot of bashing these days. Take this more as proof of concept. I would not recommend anyone to buy this. And I think they can immediately design a drug with this. So we give RL feedback, we get our sample 3D conformer, we put it in this case to a software called Quick Viessmann, which is a very fast docking way. There are more precise ways, but here we're having this in the training loop, in the DDPO training loop, so we don't want to waste too much time. This model will start to dock the conformers and assign it docking scores, which we can use as rewards. Okay, so now we already get some feedback on what makes a better ligand in terms of binding to a pocket, but we want to make this even more concrete and useful toy model. So this is work that I did with my colleague Alba Jimenez at Flagship. She's a fantastic systems biologist, and she was like, hey, why don't you test this on PARP2? So PARP2 is a cancer target in the CNS, in the central nervous system, and an ideal inhibitor, so you want to inhibit this guy. An ideal inhibitor needs high binding affinity to PARP2, and ideally only to PARP2 and nothing else, but also needs to make it there. So you can actually, it's not that hard to design a molecule that is very sticky and binds to everything, but then A, it will bind to everything, not just your target, and B, it will unlikely for it to end up in the brain, which is very selective in terms of Dalton weight and what the molecule looks like. So here we had an additional reward model that was predicting blood-brain barrier penetration. And we used our generative model. Remember, that's the diffusion model that diffuses ligands into protein pockets. We give it feedback on docking, we give it feedback on blood-brain barrier permeability, and then compare it to the data that we know. And before I show you the results, something I want to tell you, I think very important lesson learned here. If you have multiple rewards, it can sometimes be tricky to optimize them both at the same time. And there's also a limit to multi-objective, a theoretical limit on how much you can optimize at the same time. I often found if I was to just optimize for blood-brain barrier permeability, I got catastrophic forgetting, so I tried KL penalty, but in the end I was just walking back and forth, didn't see improvement on both ends. What worked way, way better for this was an iterative back and forth over the diffusion steps. So you do a couple of steps of just the diffusion, so that's your original policy, and then you switch and do a couple of steps of your optimization on your proxy rewards like blood-brain barrier or the docking, and then you switch back to your original diffusion. And doing this allowed me in practice here to walk this Pareto front and to produce these results. So for PARP2, it's a popular target, so there actually exist 24 ground truth structures, natural ligands. If you put those into the docking, they give you an affinity score of -10, that's fairly high, but they're not very permeable, so the permeability model tells you the likelihood is just 4% on average. If we now take our RL version of the small molecule diffusion, we also generate 24 ligands, to be fair here, put them into the docking. They have a similar affinity score of -10, but now the blood-brain barrier permeability is at 45%. I want to emphasize here that this is all just in silico predicted properties, and always want to emphasize this is not taken as valid or proper solution. There are many more things that need to go into a successful small molecule. One thing that I found interesting, if I just looked a little bit closer and what did the reward tuning actually do to the solutions, to the molecules, it made them lighter. It shows atom types that were lighter in Dalton weight, and that kind of makes sense because it's the lighter compounds that make it through the brain or into the brain. Okay. I have 5 minutes left, and I think that's enough. So I talked a lot about policy gradients, and that's a very classic old school way of doing RL, but it's not all that is out there, so I also want to touch upon a more recent approaches, which is, in this case, generative flow networks in the case of antibody design. So just to prime you, For the previous method, we had a pre-trained policy, and then we would do this RL tuning. The generative flow network approach has the feedback or has the reward distribution already during the time of the generative policy in it. And I'll show you this after this slide with an equation. But first I want to introduce you to the problem, because I assume not too many people are familiar on what makes a successful antibody. So antibody-antigen design is about getting the CDRH3 right. And I'll explain this to you. So what you see here, the guy in yellow, that's influenza antigen, H1N1. And it has this 220 loop here. And this guy to the left, like the green and blue, that's an antibody. It's fairly big. It's a big protein, or decently big. But the part that binds, and that's what you want to do, you want to bind the antigen. The part that binds to this antigen loop is these CDRH3. So R stands for right, there's also a left one, and H3 is because there are 3. So it's this loop, and also if you look at antibody structural data, these loops, they're very floppy. They're almost like floppy fingers that can nicely snug into the antigen that makes them bind so nicely. Structure is also harder to predict because there's not as much data on this available. So in practice, it's really about getting this loop right. So antibody design often reduces to the design of the CDRH3 loop, and you have a fixed framework. This is a stretch of 10 to 30 amino acids, which sounds short and somewhat easy, but it's absolutely not. And a lot of people are behind antibody design. You see a lot of money being raised also in startups in this domain. So it's a hot topic. So why can I not just take a conventional protein LLM to fill in the blank for the CDRH3 loop, especially if I have a fixed framework of the rest of the antibody? There's a lot of context. Generally, protein LLMs, for example, ESM, are not very good at modeling these antibodies, because those are somewhat out of distribution, and it really matters to get everything exactly right. So that's not a straightforward solution. In practice, what people do, they do a lot of screening, and there are people that really have expert knowledge in what these stretches look like. So usually they design the loop, and they know exactly already a position. 1, 2, and 3 have to be ARG. Then I have a variable stretch of 4. Then there has to be a Y. And then they start to mutate around those variable positions. And then they take those candidates that were kind of like manually, smartly educated guesses and take them to the lab and get feedback. So here we wanted to test different reinforcement learning methods to propose new CDRH3s with experimental data and a reward proxy model. So the data that we took is from an alpaca data set, so you actually won't find that much antibody-antigen data online. There's not a lot of public data. I also assume that Big Pharma, if they have it, they will not make it public. But this is alpaca data where they immunized this alpaca and then screened the antibodies that it expressed and checked which ones of these bind to this IL-6 antigen that they immunized it against. So we can use that data to generate a reward model that basically tells us the likelihood of CDRH3 to bind. We can then take our CDRH3 generator, and in theory, you want to get this into a lab loop. So you want to predict stuff, get more experiments, update your reward model, and so on, and take that to a loop. That part we didn't do. But I want to talk about the methods and which one might be better here. So let's compare policy gradients and generative flows. So to model the CDRH3, we're not going to do this with a transformer approach. We're going to do this with an autoregressive discrete diffusion model, because you can treat the next token prediction as a discrete diffusion step, right? Where you predict a token at time t-1, given tokens at time t. And this can be done left to right or any order, as I previously explained. So this is what it looks like, and then you can, as we did before, you can define the DDPO step to give feedback on if this sequence binds to the antigen according to the reward model. So generative flows. Generative flows, they do not pre-train a policy and then fine-tune it. They already bake the reward distribution into the generative process. So this is work done by Joshua Benjo's lab. I think it's actually first and last author of Benjo. I think it's his son who's the first author, and he's last author. So generative flows are an alternative to policy gradients with promising properties. They promise to be more diverse, and most importantly, they promise to not collapse to a single minimum. Because if you and you should read the papers, I'm not going to go over all the details. In GFlowNet, the sampling will be proportional to an arbitrary reward. So the likelihood of sampling X, or in this case of generating a sequence, will be proportional to the reward distribution. And the way that it's done, you see this diagram here. I hope it's not too small. I hope you can see this flow here from one node to the other. So if you look into flow matching, you know you can, diffusion is a type of flow matching. So you can kind of like see the analogies to diffusion approaches. You start in the beginning with your source distribution as naught. And now there are these different nodes, and there's an associated flow from that region as naught to its nodes, and you can imagine these could be, you decode your first residue, then given that one, you decode your next residue. And this flow here from S naught into the other nodes and so on is the total sum of all of your rewards. So at the beginning you have you're like Santa, you have like your big bag of all the rewards, the good ones and the bad ones. And all of these are being distributed across the different solutions, and at the end state where you have completely decoded the sequence, you assign your reward. Is that a sequence that binds or that doesn't bind? And a way to train that is very important. Is the rule is the inflow at a node has to match the outflow at the node. And if there is anything that I want you to take away from this slide, it's actually just these two red boxes. Policy gradients maximize rewards. That's how they tend to focus just on one win. Whereas the generative flow policy approximates a reward distribution indirectly. So it will generate sequences that are good rewards, but also non-binders. But that way you get diverse solutions and you do not collapse, and you can continue exploring. So this is a bit of a complicated slide. It's also my last slide, but I'm going to talk you through it. So does it deliver on what it did? Because I said in the beginning, we tried these different approaches. We just wanted to test them. Do they really work how they're supposed to work in theory? What we find is that the GFlow approach samples more diverse solutions compared to the policy gradient approach that actually just ends up maximizing the reward and becoming very single-minded. So what you see here is a UMAP of CDRH3 loops. I think that's cut a bit. So these are the CDRH3 loops. This is what they look like. It's this 12, 14 amino acid residues. They can be variable length. And every point here is an embedding of the CDRH3. And the ground truth from this alpaca data set that we use to train the reward proxy, these golden stars here, those are the true positive binders. So there's a big patch here, there's one down here, and then they're a bit spread. The blue one are the true negative binders. And what we find is for the policy gradient method, which is the ARDM generated one, they all just cluster on top of here. And actually, we think these are reward hackers because the gradient, the policy gradient really just wants to get a likelihood of binding that is 1. And it finds it, and that's likely actually just exploiting the reward model, which is a very simple model. It's been trained on a couple of thousand data points. They're very easy to hack. That's generally a problem with all of these methods. Don't overestimate your reward proxy model. They're very easy to hack and satisfy. Whereas we find for the GFlow generated ones, they're more spread out, and we find some that overlap with the true positives, but we also find some that are more at the rim of the distribution. We actually don't know what's going on down here. But if we look at the sequences, so this green arrow here is a generated with GFlowNet, has a binding probability of 94%. If you pick a true positive nearby, they share some of the motifs, similar binding probability. So we concluded in this case, maybe using GFlow net training is a better way to approach this problem. And with that, I'm very close to over time. I want to come to my last slide, my key takeaways, and actually they're more like spicy opinions. So first of all, I think reinforcement learning in biology is rather understood as reinforcement tuning. We cannot bootstrap biological intelligence from scratch, because data is sparse and simulations are expensive or not good enough. As I don't know if someone went to the neural operator talk from yesterday for the MD simulations. If those were cheap, our problems would be solved. We wouldn't need RL. Second takeaway, generative biomolecular design still benefits from RL as a black box optimizer in many settings. Could be that you have non-differentiable rewards like experiments or other preferences, or your feedback is a very big model where you want to bake in the heuristics of that model into your original policy. Another point which I think had touched upon in his previous talk, RL tuning is an art. And hyperparameter optimization usually also won't get you very far. And had it in his previous talk, he had this long list of all the engineering tricks that went into successful training. And if you often look at training loss curves, they're really, really like, it goes down and it massively starts to oscillate, go back up, which makes HPO really hard. And it, at some point, it actually feels like you're engineering so many knobs, you're kind of like hacking yourself to success. You're just trying to find all these like fine-tuned parameters to actually maximize some reward, and that's really frustrating. And that's also why me personally, I'm not convinced of RL in biology. Today, I have not seen any instances of very smart exploration by RL, and I think this is in part because also the solution space might not be very smooth. So what I mean by smart exploration, that the RL-tuned policy would give me like a very, very novel protein that looks very different to the solutions that we know, or would give me a small molecule that is like really far away from the distributions that the feedbacks were coming from. However, I have seen many instances of mode collapse and proxy model exploitation at the expense of solution diversity. And this is really where, you know, you're only going to be as smart than your proxy model, because that's all your feedback is coming from. So if your proxy model, like docking, is meh, you'll distill meh into your generative model. I think experimental feedback might be more interesting, but experimental feedback is also very slow. So overall, that's my spicy opinion. I think RL tuning is in principle pretty dumb because it's black box. It does what it says on the tin, it's black box optimization, but it is not a very smart way of finding novel solution spaces by understanding the mechanisms or really trying to model the true data distribution. However, it is somewhat the best thing that we have until today to deal with solutions where we have lack of data. So it is a short-term solution to fill the gap of lack of data. And with that, oh no, that was too far. My last slide, come on. No. Okay, yeah. Last point, I want to thank you for listening. Here's my contact. It's Viessmann@flagshippioneering.com. I want to say a special thank you to Yasha and Sid, who contributed a lot to the work, especially the categorical diffusion for inverse folding. These are just pictures from our group in Boston. So we are constantly hiring into the pioneering intelligence team and also into our startups. We call ourselves scientist entrepreneurs. So if you're excited about really fundamental machine learning research, but also want to put it into impact by contributing to starting companies, please contact me or check out also our website for opportunities. And yeah, thank you. So I'm open to questions. Maybe I can.
You know, by the way, what in silico genomics, what algorithm do they use?
In silico genomics?
Yeah, in silico.
So I have not seen RL applications for genomics, and I think that's maybe.
Synthetic drugs.
Oh, in terms of proxy?
Huh?
So all I know about like generative methods would be like using like long context like Mamba to generate genomic sequences, and I have not tried to RL tune a DNA Mamba, but might be interesting maybe for phenotype or disease expression, but I don't know of any proxy or data. If you do, let me know because I'd be interested too.
Okay, thanks for an interesting talk. So in this inverse protein folding, when we know that same like very different sequences can generate identical structures. So when you give a particular structure, are your model generating always the same sequence if you run forward?
No. So yeah, you're touching on a very important point. You want to have a policy that can generate diverse outputs for a fixed one given input. So we generate diverse solutions. There are two, depending on what your approach is. In the case of autoregressive methods like protein MPNN, one way to create diverse samples is by just randomizing the decoding order. So if you change the decoding order, like that will change the sequence that comes out of it. Another way that people like to do, and I heavily want to tell people not to do it, doing temperature sampling on autoregressive is a way to diversify your sequences as well, but at the expense of quality. So very easily you'll pick something that will dramatically unravel, or at least according to in silico methods. So yeah, we usually any order decoding. A colleague of mine did some fun experiments also trying to put noise onto the weights of the model. That's also another way to diversify. You could also add noise to, add a little bit of noise to your input structure. But there are many different ways to get diverse sequences, yes.
And how different will be the predicate template models for example, in the case of the tribe?
Yeah. We actually, so we're currently, we submitted our work and we actually have this graph in there where we look at TM score as a function of diversity. So the diversity that I quoted of 45% was measured at a TM score of 0.7. And we chose 0.7 because sometimes biologists say 0.7 is the threshold for being of the same fold. Yeah, I can also afterwards I can send you that graph.
Thank you.
Thank you for interesting talk. My question is again about protein reverse folding and diversity. So do you see any correlation between the diversity, places where you can change the amino acid, and the PLDPT value? The second thing, whether you can change the amino acids where two very far from each other amino acids come to contact.
Very interesting question. We have not done it. I have not looked into diversity as a function of PLDTT, but I would suspect it because usually PLDTT is particularly low in those unraveled regions and in the disordered regions, exactly. Which and it might actually be biological truth that it's very diverse in these regions. And it might also have interesting functions. So your question, I think, is a valid analysis we should look into. But no, I haven't done it. And then the second question was if we have two residues that are far in sequence space but are close nearby in the folded 3D space. And the question was, in that case, if they mutate together, or?
No, you can if you can change some amino acid, like one of these two contacting amino acids.
You could force that. So with most of these methods, so with, for example, with a categorical diffusion, because you're decoding each individual one, you can fix if you want. So if you want at position 0, you want a certain amino acid there, you can fix that instead of predicting it. The same with position 7 or whichever you want. Is that the...
If alpha fold then folds the protein, yes, this answers my question.
Okay. And it's actually an interesting use case. Often people, they want a fixed part of the structure and then just similar to the antibody case, they just want to redesign a specific part.
Because in disorder regions, you don't want diversity because you can change any of the amino acids because it is disordered region.
Yeah. Yeah, what we're also interested in doing soon is we want to look at the residues that are hydrophobic and hydrophilic, look at like the inside versus the outside surface, and look at the packing and how it's changing there. So that's also, I think, very informative for the protein designers. Where is the true diversity? The interesting thing with it is no one knows the ground truth because no one knows what actually could exist in biology. So it's the same with the TM score question. We don't know what is, for a given alpha helix, how many sequences are there? We don't know. We know there should be many, but we don't know how many.
Thank you for comprehensive talk. Yeah. It was very interesting. So I'm a complete stranger to the field, so sort of the tough questions. I was just curious about like the training process. You mentioned the policy, and then the tries to estimate the distribution of the reward indirectly, and then there is direct reward optimization with the reinforcement learning based fine tuning. So I was just curious whether there is line of work that is trying to incorporate the reward into the policy training as some sort of loss regularization, so you potentially can get rid of the costly reinforcement learning based fine tuning part.
Yes. So maybe first answer, you can incorporate diversity also via entropy methods into the loss, but I don't think that's what, I think what you asked was, can you incorporate the loss into the original policy training?
Can you basically make the loss be regularized with some rewards or scores generated by the scoring model that, as far as I understand, you mentioned, I think you call it a proxy model, right?
Yeah.
That you basically, you have that model. I'm actually not sure that I understood where the model is coming from, but basically if you
It's another trained model,
yeah.
or directly like a human that gives the reward, or it could be an experiment.
So theoretically,
It's an oracle.
You have some training data for your policy model. Theoretically, you can basically pass that data to your policy model, get some rewards, and incorporate them somehow to the loss of the.
Yeah. I think maybe what gets at your question is, so one thing that is also actively done, first you can take your ground truth data and you will just calculate the log probs under the given policy and give that as feedback. So you're not generating, you can recycle the experimental data into the training. But I think maybe what you're asking for is actually this G-flow approach, where now there is no difference anymore between pre-trained policy training and subsequent RL fine-tuning. The rewards are already baked in into the from-scratch policy training. And the reason is that this flow mass that has to be matched at each node is proportional to the rewards that are being assigned at the very end. That's basically if you have like a high reward, so at the end of each of these nodes are the rewards either from your oracle or from your experiment or whatever. So this policy will generate samples according to your reward distribution. It's just one training.
Okay, I think we're over time now. We have lunch going, so that's it. Let's give another round of applause for Olivia.